Hi everyone. So we will be looking now at the rest of 10.1. This is a continuation of what we did in class. So during the lecture, we introduced hypothesis testing for two population means. We looked at the assumptions and then we actually conducted a hypothesis test. And we specifically looked at the scenario where both populations were normally distributed with known variance, and we called that case 1. In this video, we're going to look at case 2, and then we'll also look at other special calculations. So overall, by the end of 10.1 and 10.2, you would have covered 4 versions of tests for mu1 minus mu2. So you need to make sure you can do all of them for all 4 cases. You will also need to make sure you can calculate confidence intervals for all 4 cases. We won't necessarily do each and every one because the procedure is the same, but I will show you the pivotal quantities. They are in the summary, and you need to make sure you can do both the upper, lower, and two-sided confidence intervals. Then you'll also need to make sure that you can calculate the probability of a type 2 error, as well as finding sample sizes given certain information, but this is only required for case 1. In class, we were looking at exercise 5, and we didn't quite finish. There was the bonus question, which I am going to cover the rest of in this video. And then I gave you homework exercises 2 and 6A, and those memos are already available on ClickUp. Exercise 6A, rather exercise 6, now the whole question, it's got extra parts. You will be able to complete it by the end of this video. Okay, so this is just a recap. Remember, this is the spreadsheet that I gave you during the lecture. It is available on ClickUp, and it's just a summary of the important results that you need to know for this section. So if you're able to follow this flow chart, then you'll always know which hypothesis to do when. During the lecture, we started off with the basic assumptions where you have two independent populations and the observations themselves are also independent. So you have independence all around. And then we asked ourselves, okay, in the scenario that we're given, do we have equal variances or are the variances known or not? And we looked at the special case where the variances were known. And then in order to apply the hypothesis test associated with this quantity here, we needed to also double check that the two populations also had normal distributions. And then in this scenario, once we had that, then this was I mentioned it would be your pivotal quantity for a confidence interval, and then for a hypothesis test, you'd replace mu1 minus mu2 with whatever value of delta 0 you have. That's your null value. In this video now, let's quickly have a look now. What if you don't know the variances? Then the next question you're going to ask yourself is, okay, what are the sample sizes? And if you see that both M and N are greater than 40, then you end up with a case 2. And then this ends up being your pivotal quantity, and then you can modify this for your test statistic. And you can see these two things are very similar. They're both normally distributed. However, since the variances are not known, then you need to take the estimates. So that's what you're going to put in here. And then another thing that you'll also notice that is different is that in this case, we needed to make sure that we had normality in order for this to hold. Here, the normality is there, but then it comes from the central limit theorem. So whenever you need to apply case 2, you don't necessarily need to have the two populations being normally distributed. They can be absolutely any distribution as long as the sample is large enough. The central limit theorem tells us that the data for x bar, if you calculate x bar and y bar, it's approximately normally distributed. So that's why it looks similar. So notice here, in this case, there's no restriction on the sample size if you have normality. And then when you have a large sample, then you can use, it doesn't need to be any particular distribution. So in class, we introduced case one as follows. We have your basic assumptions of that of independence, and then we said normality in the populations, and then we also said that sigma 1 squared and sigma 2 squared are known. So in case two, now it's a large sample and then it's unknown variances. And then the only difference is your test statistic. So your null remains the same, your alternatives, rejection regions, and your p-value calculations are identical. The only difference is now how you're going to calculate your test statistic. Let's now have a look at objective 2, which is that of deriving confidence intervals and also doing the calculations. You need to make sure that you're able to do it for all of the 4 cases for the differences between the means. In this video, I'm going to do 2 derivations. I'm going to do a two-sided and a one-sided case, but you need to make sure that you can do it for all of them. The procedure is the same, so if you can do one of them, you should be able to do the rest. The only difference would be your pivotal quantity. So let's have a look at this example. So we're given 2 random samples, one of size m and the other one is size n, where m is greater than 40, n is greater than 40 as well. The variances are known, and also note they are independent populations. Okay, so we need to calculate a 100 1 minus alpha percent confidence interval for mu1 minus mu2. So whenever you need to now calculate this two-sided confidence interval for mu1 minus mu2, the idea you need to keep in mind is we want to have some interval inside such that the probability of mu1 minus mu2 being in that interval equals 1 minus alpha. So this is what you want to keep in mind. As we do our derivation, we want to end up with something like this, and we just need to figure out what those question marks should be. So now you need a pivotal quantity in order to even start this derivation. So in order to determine it, you can go to your summary. You won't have this in a test, but I'll show you in the next slide how you will figure out your pivotal quantity. And then you need to make sure you identify which scenario you have. So all of these variables here are you're going to be pivotal quantities for the respective cases. So let's have a look now. This is a summarized version. In yellow, I have the assumptions. So just to help you remember, this is a condensed version. So if you remember this, you should arrive at the correct case, regardless of what question you get. So remember, you always check for independence. That's your basic assumption. That is required for all of the tests. If you do not have independence, then you must not use any of these. You're going to use a different test, which we're going to cover in 10.3. So the moment you see you have 2 populations and they're independent, then you're going to check, do you know the variances or not? If you know them, then it's possibly a case 1. It will definitely be a case 1 if you then find that the data comes from normally distributed populations. And then on the other hand, if you now realize you don't actually know what sigma squared is and you have to use the estimates, then you need to first verify that are the sample sizes large or not. And then a large sample size is when when m and n, both of them, are greater than 40. If they are, then you have case 2. So notice here that here I don't have that assumption of normality the way I have it here. So the reason for that is because when you have a large sample size, you can assume the central limit theorem holds. So the normality is implied. So here, this also means that your data doesn't necessarily need to come from a normal distribution. It could come from a Poisson or a gamma, any distribution, as long as the sample size is large. And then you'll notice that when you get to case 3 and 4, that normality assumption comes back again. So you need to make sure it's there before you apply these results. And then now if you look at your formula sheet, the different cases are provided, but it's not the test statistics. The pivotal quantity, it is the test statistics. So if you want to do a hypothesis test, then these are your test statistics. And to get your pivotal quantity, remember that delta 0 was put in place of mu1 minus mu2. So in all of these cases, if you put mu1 minus mu2 in place of your test statistics, that will then give you um, your that'll give you your pivotal quantity, sorry. And then you can, it's not going to mention whether it's case 1, case 2, 3, or 4. I'm the one who added these labels, but you will be able to tell this one is obviously known variances, unknown variances, and then you'll learn a bit more about these a little bit later. Okay, so if we come back to our problem here, in order now to pick the correct pivotal quantity, we'll check which scenario we have. So first things first, do we have independence? Yes, we do. So we can use this. And then the next thing is now we check, do we know the variances? It says no. So we move down to the next branch, and then we now need to check, do we have large samples? And we do. So therefore we move to case 2. And remember the case 2 pivotal quantity, it's this one with mu1 minus mu2 in there. So it looks exactly like that, and it has a standard normal distribution. So this is your pivotal quantity, and then now your starting place. If you now use a standard normal, you know that the probability of z being between these two values is 1 minus alpha. So what you'll do from here is you'll substitute z into the z position there, and then you will now manipulate what's inside. So you're only left with mu1 minus mu2 inside. So here we've done the substitution now. So the manipulation in this case will involve multiplying both sides of this equation by the denominator, and then you'll subtract x bar minus y bar from both sides, and then you'll end up multiplying minus 1 throughout, and that's going to change all the signs and as well as your inequalities. So at the end of the day, this is the result that you'll get. And what's inside here is your confidence interval. And you can write it more concisely in this form. So you end up with x bar minus y bar plus minus z times your standard error. And this is actually a case of the general formula for a confidence interval. So you'll see you have your theta hat, which is x bar minus y bar, and then it's plus minus your critical value, and then this is your standard error. So remember, standard error is just another way of saying variance of your statistic or your estimator, which is x bar minus y bar. So that's where this comes from there. Now, if you have this result, then you can figure out your one-sided confidence bounds without doing a full derivation, but you should be able to do it. But if you just need to do a calculation, then this is the easiest way. So this is from your textbook at the top of page 495. For an upper or lower confidence bound, you can calculate them by retaining the appropriate sign and replacing z alpha over 2 by z alpha. So for instance, for an upper confidence bound, remember you want an upper value, so you're going to use the plus sign. So you'll drop the minus, and then in place of z alpha over 2, you'll have z alpha. Similarly, for the lower confidence bound, you'll replace the plus minus with the minus sign only, and then this will be z alpha. So you'll only calculate one value in the one-sided cases. So if we refer back to example 5, this is exercise 5, and we did it in class. We did A and B, and then I threw in a bonus question where I wanted you to do this hypothesis test using the confidence interval. I had hoped to do the derivation during class, but no worries, we're going to do it during this video. So in class, we covered A and B. We did the whole test, which is here if you want to verify your own answers in case you missed anything. I'm going to focus now on the hypothesis testing part. So I want you to calculate an appropriate confidence interval to test this hypothesis. So it could be upper, lower, two-sided. You need to determine which one will allow you to make a decision at the end of the day. So there's obviously your three alternatives. And in order to determine which test you need, you just first need to identify, okay, is this a one-sided, is it upper, lower? So let's do the first one together. So this is called an upper tail test. It's upper tailed because the rejection region consists of values that are large. So you reject for values like on the upper tail of the distribution. So you can think of it that way. And then the appropriate confidence interval to test this hypothesis is this one here. You need to calculate a lower confidence bound. So I called it LL. So that's going to be the value that you need to calculate. And then for the other ones, notice for the lower tail, you swap it. You need to get the upper confidence bound. And then for the two-sided test, it's a two-sided confidence interval. Okay, so just watch out for these ones where you need to just swap them around. Okay, so let's have a look at our example. So we were given that mu1 minus mu2 is less than minus 1. So this is an example, therefore, of a lower tailed test. So if you look at the sign, that's what I'm looking at. This one's less than, less than. So it's a lower tailed test. Therefore, we need to calculate an upper confidence bound. So in order to calculate an upper confidence bound, so the shortcut is using that hint from 494, where if you want the upper side, we need to take the positive sign and then change this to Z alpha. So this is what you end up with. So I want you to work it out on your own. Go and get X bar from the question, Y bar, Z alpha from the table, and substitute the relevant values. And then you can verify your answer. You can pause the video now if you don't want to see it or if you haven't done it. And now the answer therefore is going to be this. So the confidence interval is from minus infinity to minus 1.080. Okay, so but this is not going to give us now your decision. So in order to get your decision, let's quickly see what we do. So this is my summary that I did with you in class. I have uploaded it on ClickUp as well, so you can make sure you know it well. We're doing the confidence interval case. So when you are doing a hypothesis test using a confidence interval, then you need to now check whether theta 0 is in the confidence interval or not. So note well, it's theta 0, which is your null value. It's not your test statistic value. A lot of people make that mistake. You check whether this value is in the confidence interval or not. If it is not in the confidence interval, then you must reject the null hypothesis. So let's go see, is it in the confidence interval or not? So here our null value is minus 1. And minus 1 is not in this interval. Therefore, we're going to reject H0. And this should coincide with the test that we did with the test statistics. I'm going to go back. See, you get the same result. So you should always arrive at the same conclusion, whether you use the p-value approach, the test statistic approach, or the confidence interval approach. We can actually move on to now the actual derivation, which you should be able to do. So let's see how we come to this result, but using the derivation approach and not going straight from here. So you always keep your target in mind. So when you want an upper confidence bound, you're going to have whatever your target is. In this case, it's mu1 minus mu2, and then you have your upper limit. So that's your UL equal to 1 minus alpha. Now you're going to need a pivotal quantity. So you need to determine what case this one is. And we went through this question 5 as an example of case 1. Therefore, this is your pivotal quantity. Now, from here, your starting point is going to be z greater than something equals 1 minus alpha. So notice this is greater than, here it's less than. And the reason for that is once we put z in here and manipulate everything, notice that there's a minus sign over there, which is going to flip the sign over so it ends up facing the correct direction. So you need to start on this side for the upper confidence bound. Now we need to find what is this value represented by these question marks. So it's a normal distribution. So what I would do is draw a sketch. And we're saying that there is some value such that the probability of z being greater than that value is 1 minus alpha. So we can split our distribution so that we have 1 minus alpha on the right. So we're saying this area is on the right because it's that greater than sign, so it's greater than. And there's some value. So we know using our critical values, definitely the area in the subscript is the area on the right. So you could have 1 minus alpha. But if you want to get the result in the that we used just now, then you need to use minus z alpha. So remember, because of symmetry, if you were to reflect this, you would have z alpha on this side. But then remember, standard normal is centered at 0. So this is the negative version of that positive value. So that's how you get minus z alpha. Okay. So just draw a sketch. You can even mirror it and you'll see. So this value in here is minus z alpha. And now to complete this derivation, we just need to substitute z in there. And then we need to manipulate this so that we end up with mu1 minus mu2 on its own on the left-hand side. So keep your target in mind, and then I just rewrote it the other way around. I put 1 minus alpha on the left instead of on the right so that I don't have to keep on writing it. So I can just keep on saying equals to equals to. So in the next line, I just go equal to. So I'm continuing from here. I multiplied both sides by the denominator, so it came here. And then I subtracted x bar minus y bar from both sides. And then now you have this minus sign. We're going to now multiply throughout with the minus sign. And then that's going to make this positive. That's going to be positive. And then also the sign is going to change. So ultimately now we have it in this form. So this is actually our upper bound that we're looking for. So this leads us to the exact same upper bound that we used to calculate the answer in question 5. So this will complete the proof if you're asked to do a derivation for the upper bound. Let's now have a look at objective 3, where we want to be able to calculate the probability of type 2 errors for case 1. So I want to do just a quick recap so you can understand what exactly you're doing when you're calculating a type 2 error. And I want to show you visually. Hopefully it'll help you understand. So a type 2 error is when you do not reject H0 when in fact H0 is false. So let's take a look at this example. It's from chapter 9, but I feel like it's the easiest to really understand this whole idea. The idea is the same as well for chapter 10, but let's use this as our recap. So remember now, with your null, this is the one you're assuming mu equals to a specific value. That's your null value. And then your alternative is mu greater than that specific value. And when we conduct a hypothesis test, we always do it assuming that the null is true. So here, this blue curve is the one represented by the null. So notice the mean, mu0, is the center of this blue distribution. And then now when we want to conduct the hypothesis test, we want to reject whenever we have z values greater than z alpha. So this is your test statistic greater than your z alpha. So z alpha is just that value that cuts this blue distribution so that the area to the right is alpha. So z alpha is over here under the blue curve. this little bit is your alpha. So if you're given 0.05, that's the 0.05, and then this is the value. So anytime you have a value on this side of Z alpha, then you end up rejecting. And when you have any value on this side, then you end up not rejecting. Okay, so now if you look at this alternative is represented in this distribution now. And now you can see mu greater than mu zero actually is a whole range of values from mu zero all the way to infinity, not including mu zero because it's there. So let's say if mu zero was a value of 5, then mu greater than 5 is any value like 7, 8, 9, 10, 11, 100. So if you try to plot the distribution and have the center at 6, 7, 8, 9, 10, 11, it's going to be lots of different ones. So when you're asked to calculate a type 2 error, they will always give you a specific value, and that's going to lock the distribution. The specific value is going to be mu prime. So when they say mu equals mu prime, that's going to be equivalent to H0 being false because it's going to be some value that's going to be, in this case, in the alternative, satisfying the alternative. So let's say the alternative is true. So mu equal mu prime, then you end up with this green distribution here, and then mu prime is the center over here. So when they say they want you to calculate the probability of a type 2 error, they're saying what's the probability of not rejecting H0 when in fact the true value of mu is mu prime. So if the true value is mu prime, then the true distribution is this one. And then the probability of not rejecting, remember I said here, when you go to the right, you reject. When you go to the left, you do not reject. So that means we want the area to the left under the green curve because we're assuming that it's actually the green curve, which is true, but then we didn't reject because we didn't get a value on this side of that critical value. So the area that you're actually calculating when you calculate type 2 error is this little tail area in here. So I've seen it in a test, in a past paper where you're asked to shade in where's your alpha and your beta. This is how you'll shade it in. You'll have your ejection region, and then beta is this area under the alternative distribution. So when it comes now to our case in chapter 10, instead of mu zero, we have delta zero, right, as your null. And then for our alternatives, the one that they will give you is delta prime. So they'll specify delta prime and it's going to satisfy your alternative. And then you just need to make sure that you know which is delta prime. So if you go to page 489, you have the formulas. So if you have an upper tail test, this is the formula you're going to use to calculate the probability of the type 2 error. And then it's this formula as well for the other cases. And then notice in the denominator, you have the sigma, which is calculated using this formula here. So note these formulas will be given in your formula sheet and you do not need to know the derivations or the proofs for them. So let's quickly look at an example. So in this case, this is question 5. This is part C. This is the true C, not the one I created. In the textbook, they ask you to calculate the probability of a type 2 error when the actual difference is mu1 minus mu2 equal to minus 1.2. So notice minus 1.2 um, satisfies the alternative, but it violates the null. So we've been given a specific value. So notice this is your delta prime. And then this is your null value. That's your delta 0. And here, since it's a less than, we want to use this scenario, 1 minus this result. So we just need to identify the different parts. Okay, so for Z alpha, we were given alpha 0.01. And remember, when you have the Z with a subscript, that subscript is the area to the right. So make sure that you can go and find this Z alpha. Look for the value that cuts this distribution so that you have 0,01 on the right. And you'll find it's 2.33. And then, as I said earlier, your null value is your minus 1. And then your delta prime is the one that is given as your alternative. And then to do the calculation, you just substitute the values into the formula. So in your sigma, everything is given in the question, and this is what you should get as your final result. And then note this capital phi, you should know this is just your CDF for your normal distribution. So it's the probability that Z is less than minus 0.92. So you'll read that from your tables. If you'd like further practice, you can look at example 10.3. And then lastly, you will be expected to be able to calculate sample sizes for case 1. So there are two formulas. The first formula is this one. So this is the scenario where you're given alpha, beta, and delta prime. So you need to just see what information you're given. That'll determine which one you use. And in the scenario where you're given these three things, all you have to do is substitute them into the formula here. And then um, notice, I think we covered everything here. This Z beta is just this critical value. So in place of alpha, put beta. So Z beta is that value that cuts the distribution. So the area to the right is beta. And then notice then, so when you calculate the sample size using this information here, the assumption is that you have equal sample sizes. So you're going to get one value, which was like your M or your N, and that's going to be the sample sizes for both populations. And then this particular formula is the expression for an upper or lower tail tests. And then if you want to do the one for the two-tail test, then remember to replace alpha with alpha over 2. So just remember that modification. Once you calculate the value, you must always round up to an integer. And note, you don't have to do the proof. This result is given in your formula sheet. Then the other way of calculating the sample size is maybe the person has a particular interval width that they want. So you'll be given the width in this scenario. So you can see the formulas require different things. And if you don't have enough for this formula, you probably have enough for the other one. And in this scenario here, you will need to then also round up to an integer as well. And then you don't need to know the proof. It will be given the formula sheet again. And although I said only case 1, you'll see there's a note in the book where it says you can actually use this result where sigma 1 and sigma 2 are at least approximately known. So that's just a note. So we'll just round up with an example. So part D of question 5, you're welcome to attempt it on your own. I'm going to go through the memo, but you can pause the video and do it. So here, we've been asked to calculate a sample size where we're required to have beta equal to 0.1 and mu1 minus mu2 equal to minus 1.2. So you can see it's a scenario where we're given beta, we're given alpha, we have delta 0 and delta prime. So it's going to correspond with this formula rather than this one where you need the width. There's no widths for a confidence interval mentioned here at all. So you're going to need to make sure you use this formula. This is a one-tail test. So you don't need to do this modification. So we're going to use the formula as is, and we just identify everything. So Z beta, the area to the right of 1.28 is 0.1. Calculate your Z alpha, we did that already. And then the other things are given in the question, minus 1 and then minus 1.2. And when you substitute, you end up with 65.15, and you must remember to round up to 66. And for further practice, have a look at example 10.5 in your textbook. Okay, so this brings us to the end of this video. So in the video, we did cover the hypothesis test for case 1 and 2. And then we also looked at the confidence intervals, how to do the derivations and calculations for specific cases. And then we also did these two. So just note in your textbook, there's a little section on the top of page 500 to the square. You don't need to know what's in that section. And then in the next session, we're going to be covering cases 3 and 4. Thank you so much. I hope you enjoy this video. Enjoy the rest of your day.